Welcome to the APL quest. See APL wiki for details. Today's quest is called Go Forth and Multiply. It's really simple. We just need to make a multiplication table. It's the 8th problem from the 2013 round of the APL problem solving competition. For once, we're going to go straight to the obvious solution. Well, we can generate the indices from 1 to a certain target number, and then we simply need to provide the outer product using that argument both on the left and the right side, so both vertically and horizontally in our table, and this gives us our solution. So just get rid of the argument and we can give it a name, and now we can apply it as we want, and it works even on 0. Okay, now let's go to have some fun because this problem is already solved. The first thing we're going to do is try to solve this without using the outer product, which is otherwise the obvious solution. And there are a couple of different ways that we can do that. The first thing is to use the definition of the outer product. The outer product pairs up every element from the list on the left with every element from the list on its right. Now, we can actually use a property of the multiplication that it maps or distributes over multiple arguments. So if we pair up every element from our list of numbers with the entire list of numbers, then that will be the equivalent. So let's say we have the numbers here, and then we multiply using, sorry, we should not use outer product, we should multiply using rank, and we want every element, so those are scalars, rank 0 from the left, and pair them up with the entire vector, rank 1 on the right, using this iota 7 as both right and left argument, and that gives us our solution. So this is just using outer product in a hidden way because this is the definition of outer product for scalar operands. We can do more fun thing. I think a lot of people are not aware that if you give a vector argument to iota, then it generates all the indices of an array with that shape. This actually holds true even for a scalar one element vector as well. And now, since these are the indices, those are also the corresponding numbers that need to be multiplied together in a multiplication table. So we can simply say that we multiply across these, or we reduce each of these pairs of numbers with multiplication, and that gives us our solution as well. And there's even more fun we can have. Let's start again with these numbers, and this time we reshape them into the shape of our multiplication table. So this just gives us repetition. And now what we can see is that multiplication is just a series of additions. So on the first row, we need our original numbers from 1 to 7. On the second row, we want the numbers from 1 to 7 added with the numbers from 1 to 7 again. And on the third row, we want it added again. So this is simply the cumulative addition going down. And we can easily write that as the plus slash bar. So this is plus backslash bar. And so this is a cumulative vertical addition, and that gives us our multiplication table as well. And we can then write this as a function, wrap it in braces, replace the 7s here with the argument, and that gives us our solution as well. We can even make this tacit. We can observe that this is a function application of iota on the argument, and this is duplication on the argument. And duplication could also be written as self-concatenation, because we could express this as omega comma omega. So now we can write this tacitly as self-concatenation with iota on the right, and then this is our tacit equivalent. Let's have even more fun. Let's eliminate the iota. How can we eliminate the iota? Well, if we take 7 and use it to reshape 1, we get 7 ones. And now we can do the same thing. The cumulative addition on those, that gives us the equivalent of the iota. And then we can proceed as before. So we can write this tacitly using the same technique as before. You want the cumulative vertical sum of the self concatenation reshaping the cumulative sum of reshape with the right argument of 1. So now we can apply this and we get our multiplication table. Yeah, I know, it's silly, but it's a nice exercise and can give some insights into the relationship between the functions. And we can even take this one more step. We can, by saying that instead of 1 here, we can observe that a scalar has a total count of elements, which is 1. So we could use this as well. So let's do this step by step. We take the self-concatenation and reshaping the 1, and that gives us all 1s. And then we just need to do the summation and row-wise, and then we can do it column-wise, like that. And we can put all of this together to a single tacit function as follows. This one stays as at the top at the end, and the horizontal summation becomes at the top on the reshape. And there we go. We've got no iota, and you not even implement. Yeah, and then just defining everything in terms of cumulative additions. Okay, so we can see that it's not a problem to implement this multiplication table using other functionality than outer product. Let's take it one step further. Let's get rid of all APL operators. Now we are only allowed to use functions. Okay, how can we do this? Well, what we can try to do is we can start by generating our numbers. And now we can recycle these until we have enough numbers to fill the entire multiplication table. So this just repeats them over and over again. And then we need to multiply them with the corresponding numbers, which means the first 7 numbers here need to be multiplied by 1. The next 7 need to be multiplied by 2. So if again, we start off with the numbers from 1 to 7, and we now replicate them by 7 each. And now we can put these two things together. And those are the numbers in our multiplication table. The only thing we now need to do is to reshape them into the right shape, and we've got a multiplication table. And we can write this whole thing as a function simply by replacing all the 7s here with the name of the argument. And there we have it, multiplication table implemented only using functions, no operators, if you don't like operators. There are other fun ways that we can do this, and we can take, again, reshaping the numbers over and over, and then we can try transposing that, and then we can see that all we need to do is now we have the corresponding vertical numbers, as in when we had the outer product, and the horizontal numbers, as we had with as the right argument in the for multiplication in the outer product, and then the only thing we need to do is multiply these two together. So in other words, we can say that we take this and multiply with its transpose, and we've got a multiplication table right there. If we wanted to make this into a function, we could just wrap it again. Alternatively, we could give it a name. But there are even simpler ways of doing this, and that is by relying on APL's scalar extension. You can always scalar extend by using a scalar function together with an enclose. So how is this going to work? Well, we've got our numbers from 1 to 7, and then we can enclose that. It makes it a scalar. Now, if we pair up these two, then that scalar 1, 2, 3, 4, 5, 6, 7 gets paired up with 1, and paired up with 2, and paired up with 3. So we can simply write iota 7 times the enclose of iota 7, and that gives us the rows of our matrix. The only thing that's missing is mixing the rows into a proper matrix. And we can write this tacitly by simply removing the arguments. So we have a fork, we have enclose iota applied on the argument and iota applied on the argument. So we can get rid of the mention of the argument and make it 0.3. We need to enclose off the iota. And there's our tacit equivalent solution. Now, what you can observe here is that we are computing the range, the iota first, and we can actually break that, so to say, out of the expression by making it in the top of on iota. So we want the enclose of iota and the identity of the iota, and then we mix that, and that's applied on the iota itself. So this is a more efficient, silly solution. Finally, for the ultimate challenge is to implement the multiplication table without any arithmetic at all. So by arithmetic, we mean things like plus and times. And of course, this might seem impossible, but we can actually implement multiplication in the old-fashioned counting stick way. And there are different ways we could do it. Here is an example. Let's make it a bit smaller so we can see what we're doing. We know that iota can generate the numbers that we need to get multiplied together by using two of the same. But how do we actually multiply them? So what we can do is each of these pairs themselves can be an argument for iota. And this gives us for each one of these pairs gives us the indices of an array of those dimensions. But of course, that implies actually some multiplication. Say if we have 3 and 2, that gives us an array that has 3 rows and 2 columns, and that has 6 elements, which is because it's the number of rows times the number of columns. That's where we're going with it. So the only thing we need to know now is how many elements are there in each one. Well, if we ravel them, and then we can count how many elements are there in each one. And we just implemented multiplication table without using any arithmetic whatsoever. So we can make this into a function, and that works. Or we could make it tacit by observing that here we again have the self-concatenation, and we're applying iota on that, and then we have these 3 loops, the 3 eaches that we can fuse together, and we've got ourselves a tacit solution. There are other ways. Let's look at the numbers again. And now we use outer product, and we're going to write a custom function for the outer product, the function that just returns a value. The value I'm using here is a hash or a reference to the root namespace. It doesn't matter at all. I'm just using it as a placeholder value just to show that I'm not using any numbers or any characters, any values whatsoever. It could have been any array whatsoever, as long as it's just a scalar. Oops, sorry, I needed the selfie here. So now this gives us a multiplication table, but missing the values. We just have a scalar in each position. However, we do have the numbers as arguments, so we can write the arguments in here. And what we can then do is we can replicate using this. So we just, instead of having a single reference to the root namespace, we now are going to have one reference, two references, three references, and so on. And then we can replicate again using the left argument. And effectively, this is a multiplication. It's the replication of a replication. And here is the multiplication table in unary. We can convert from unary to normal numbers simply by doing a tally. We got a multiplication table. So this is another solution. Here's another fun one. We can take the numbers and do an outer replicate on these. So here we have 1 ones, 2 ones, 3 ones, 1 2, 2 2, 3 2s, and so on. We can already begin to see where we are going with this. Now what we can do is that we need to know how many do they add up to in total. And this is where the function where comes in. So if you do a where on each, what does where do? It normally gives us the indices where there are ones in a Boolean array. However, so for the first column, it will give us index 1, and then index 1 and index 2, index 1, index 2, index 3. But actually, what it does is it gives us this many of the corresponding index. So in the second column, we're going to get 2 ones, and then the next row, 2 ones and 2 2s, etc. And now we're done, because this is the multiplication table in unary, completely ignoring those actual values. So if we just fuse a tally on that, we have a multiplication table. It isn't quite a valid tacit function, but there are various ways around it. We could fuse these two together, and then it would be valid, or we could compute iota twice, give it as left argument and right argument to the outer product. That would also be valid. And finally, maybe for the most basic of counting on fingers type way of doing this, let's try with these numbers, and we're making an outer product on that with a custom function. And we are starting off with the empty vector. So this gives us one empty vector for every result. These are placeholders. And now we are going to take a value. I'm using the reference to hash again as just a placeholder value. And we're going to concatenate that to the empty vector. So that gives us a one element vector for each one. But we're not going to concatenate it just once. We're going to concatenate it as many times as the right argument shows. So for the columns, in the first column, we're going to concatenate it once. In the second column, we're going to concatenate it twice, and so on, as we can see here. But we're not going to just do that either. We're going to do this whole thing also as many times as the left argument says. So the first row, we're going to concatenate this reference to the empty vector, and so the first one we're going to concatenate it once. In the second row, first column, we're going to concatenate it twice, once. In the first row, second column, we're going to concatenate it once, but doing so twice, etc. And this gives us our unary multiplication table, and as before, we can insert tally to generate our multiplication table. Of course, these are all silly, and what you should be doing if you want the multiplication table is just the regular outer product with normal multiplication. Thank you so much for watching.